Okay, hello everyone. So we're going to start looking at trees in a bit, but before that, let's look at something that I didn't cover previously, which is converting from infix notation to postfix notation using stacks, right? So we've already discussed stacks, the data structure that only gets data that is LIFO, so last in first out, right? You can only add to the top of the stack and remove from the top of the stack, right? So there might be cases whereby you have an expression like this. Let's say 5 plus 7 divided by 6 times 2, right? So 5 times 7 divided by 6 times 2. And then you want to convert this to what we call, this is in infix. You want to convert it to postfix, which looks something like this. So 5, 7 plus 6, 2 times, then division there, right? The way these infix are evaluated, also discuss them in a bit. But how can we convert from this to this? Well, basically, using a stack, right? A few things need to be understood. First of all, these operations have precedence, and then there are certain rules that you have to follow. So, for instance, we already know that multiplication and division have higher precedence than addition and subtraction, and then you also have your brackets there, right? Your brackets having highest, and then it keeps trickling down like that. So, BODMAS brackets, so division, multiplication, addition, subtraction. Okay, so now when we're doing these guys, right? When you're solving a question like this, first thing is that you want to indicate your stack here, and then you want to have your output. Then you go in character by character in your infix expression, and then you add that to the stack and then pop it based on some rules that I'm going to explain as we go on. So first of all, we're going to add um our item there, the open bracket. Then next thing is a 5. Now the stack does not keep any of the symbols, any of the actual numbers. The numbers go straight into our output. So 5 will be added to our output. Then the next thing will be our our addition there, right? So I'm going to be putting the things on separate lines just so we can see them easily. We're going to have open bracket again on the next line. Then our addition symbol is also added to the top of the stack, and then there this 7 will be added to the output. So we're going to have 5 and 7. Now next thing is that we're going to have the close bracket. Now when you're converting, what you need to know that whenever you have a close bracket, right, whenever a close bracket comes in, what ends up happening is you then pop everything up to the last open bracket here. So we're going to pop this and that, right? So that's what happens when you do the conversion, right? When you're doing this conversion, when you when you push a close bracket onto the stack, you pop everything, include up to the very last open bracket there. So our stack will remain empty, and then we're going to pop that. And the only thing we're popping right now is the addition there. You can forget about indicating the open brackets and close brackets. You can add them there if you want, but let's not bother much with that. Okay, so now that we have that, right, next thing is we're going to add the division to the stack, right? Division to stack, and then our output, right? We're going to add division and the open bracket there. So division and open brackets, and then our output is going to be 5, 7 plus 6, right? 5, 7 plus 6. Next thing we're going to do, so we've done this, we're then going to add this to the stack. So we're going to say open that, and then we're going to have our multiplication, and then we're going to have 5, 7 plus 6, and then 2 there has been added to the output. We encounter another close bracket. What do we do when we encounter a close bracket? We pop everything up to the last open bracket. So we're only going to have this guy over here, right, which is then going to give us 5, 7 plus 6, 2, and then here we're then going to have the multiplication there. Since we're at the very end, we can also just pop this one out, so we now have an empty stack. Then they are going to have 5, 7 plus 6, 2 times division. By doing that, we've converted now from our postfix here to our infix, and it's actually a very simple way of evaluating these. You will find they're very simple to evaluate actually. So we have 5, 7 plus 6, 2 times then division there. So how we evaluate this is basically simple. You can actually use a stack again, right? You can actually use a stack again. So we have our stack, and then now we're going to have our expression, right? We're going to have our expression, right? So what we do here is as follows. Whenever we have a number, we insert that to the stack, right? In fact, whenever we have a number, we insert that to the stack. So we're going to have 5, 7. What's left of our expression is plus 6, 2, right? Times 1 there, right? But then what happens here is when we come and push, when we encounter a symbol like plus here, we apply it to the two elements on the stack, right? Our stack then becomes, if we add this gives us 12, right? 12, and then here we're going to have 6, 2 times division. Next thing, we push these two onto the stack. We're going to have 12, then we're going to have 6, then we're going to have 2, then we're going to have our times, and then our division there. We push this guy onto the stack, we're going to have 12. But then if we push this onto the stack, it applies. Remember, this is a binary operator, so it will apply to the two operations that it finds there, isn't it, right? Or to the two operands there. So it's going to do 6 times 2, which is going to give us another 12 there. And then we're going to have our division, and then going to have the division symbol there now, right? Division, again, it applies to the last two elements on the stack, which is this one. So it's going to just be a 1 as a result, which, if you evaluate this previous one, right, if you evaluate this expression, this is going to be 12 divided by 12, which is 1. That's how you can evaluate these guys. So you push your symbols onto this, you push your numbers onto a stack. When you encounter a symbol, the symbol will act upon the last two numbers on your stack. In this case, it was just 5 and 7, and then we compute the result there, push it back onto the stack. We load more numbers there. We find an operation there. It again acts on the last two elements inserted, in this case, which was 6 and 2. We get a 12, push it back, division there, right? And then finally, another thing that you might be given is, say, draw the expression tree. Now, we will talk about expression trees properly when we cover trees, right? But then, for the sake of time and also just an introduction, I'm going to show you how to do this using something called in order, right? In order traversal. So to do this one, right? In fact, for this one, is a simple shortcut. We're going to just use the original expression that was there, which was 5 plus 7 divided by 6 times 2. So the way I'll go about with this one is that the one that's in the middle here will be our root node. So again, when we start talking about trees, we'll talk about these more. So we have our division there as our root node. Then what is to the left? To the left is this guy over here. So one thing you should always remember is that all leaves. So in our trees we have these guys over here. So these nodes without children, these are called leaves, right? These we call them leaves. And then in our expression, all leaf nodes, when you're drawing your expression tree, remember that all leaf nodes should be a number, and then the other nodes that do have children, those should contain our operation. In this case, we're going to have our plus there. Just a moment. Okay, sorry for that. We're going to have this guy as well, the multiplication there, as our node there. And then what two operands are here? What two operations are being done here? The two operands, sorry, are 5 and 7. Here it's 6, and then there it's 2. And then this is an expression tree. Funny thing is, first time I drew this was during a test. That's the first time I encountered an expression tree, and that's the first time I drew it. So it was just guesswork. But after reviewing it, this is actually how I found out this is how you actually do them. And when we're using in order, right? In order traversal, which again we'll cover in depth when we start doing trees. But what you need to know is that when you have this root node in binary trees, when you have your root, and then you have the left child and then the right child here, right? You have 3 modes of traversal. You have, first of all, post order, right? Post order is oh sorry, it's pre-order first. You have pre-order, right? You have pre-order. Pre-order is where You run an operation on the root node first. So whatever operation we have, in this case, let's say it's print, run our operation on the root node first, and then we go to the left, right? We go to the left child, then that left child, and this is recursive, right? This is recursive. We run an operation on the left child. We run an operation on the left child. Now that left child now becomes the current root node for its subtree. So we run the operation of print on it, and then we go down now to its left child, which now becomes the root node, and that. To represent this as pseudocode, is basically, if we say pre, and then we take in a node, we're then going to have something like, how do we do this? It's going to be an action on the current node, right? An action on the current node, and then we're going to have pre, right? We're going to traverse now the node dot left, node dot left, right, the left child, and then we're also going to traverse the node dot right. And since this is recursive, when the left node calls the pre, in fact it's supposed to be traverse anyway, when it calls this function here, pre, what happens that when it calls it, in that instance of it, it now is the one that becomes the root node. In that case, it will do the action on it, and then we're going to call the left child of it, right? So in this case, left child, the left child now here, it does we perform the action on the left child, right? And then afterwards, since it has no more children, it goes back now this side. This guy now, for this guy now, in its instance, we've already done an action on it, and then on the left child, then now the right child will do the action. The right child has no children, so it goes back to this guy. Now for this guy, where we originally started, we did an action on this guy, and then we did on the left child, of course. Now we're going to the right, again to the right, an action on this guy, an action on the left, an action on the right. So this is pre-order, where we perform an action on the root node, and then we perform actions on its left and right child. You also have in order, whereby you say uh, you traverse the left child, then you perform an action on the current node, and then you traverse the right child. Again, these are all recursive, right? This is actually the node there, right? These are all recursive, right? So you do in what the traversal would be, we go left left, we do an action on this one, then it goes here, does that action, right? Then it comes back to this one, it does that action, then goes here left, does an action here, does the action here, comes back. In our case, for the expression tree, if we wanted to actually turn this back into an expression, we'd use in order traversal, where we say, okay, we start at this node, right? Recursively, we go to the left. This now becomes the new root node. Recursively again, we go to the left, right? This one has no left child, so what happens? We execute whatever is here, and we get 5. From there now, we go to the what's this? Since this one is done its execution, we go back to this one. This one we've already, for this one over here, we've already executed the left. Now we can execute it, which is plus, and then now we can then do right, which is save, since this one has no left or right child, we just traverse it, right? And then we're then going to come back to it now and say, since we've done this subtree now, right? We've already done this subtree. We then go to this guy. This guy is now executed, divided by, and then we go to this guy. Multiplication here becomes our root node, but then we have to explore the left first. The left has no left child, so we explore it, which is 6. There's no right child, so we take back execution to multiplication. We've already done the left part of multiplication, so I'm just going to multiply, and then we go to the right, which is 2. And this is in order. Again, these will make more sense when I actually do them in depth. This is just a brief overview, at least, to get your brain asking to say, what's going on, what's this guy writing, right? So yeah, this is this simple question, but then now we'll start trees. So let me pause this video, because to copy this train I'll talk about your as well. So let me just pause this and then go to the next one.